Yeah, thanks everyone. It's very happy to I feel very happy to have this opportunity to present on my recent work with my supervisor Simone and postdoc Huner from Caltech and Professor Davis and Stoffen from Caltech. Um, we did something about using causality to put some constraints and corrections to Einstein gravity. So this presentation will go like in this several parts. First, I'm gonna briefly introduce a bit on what we mean by modifications to Einstein gravity. And then I'm gonna review a little bit on what it means by causality and unitarity bounds of effective field theory. And then I'm gonna introduce our understanding of causality of gravity, and in the end present some new results and some summary and outlook for future directions. So if you have any question, please just ask, interrupt me, ask. So we all know that Einstein gravity is really successful, and it's especially remarkable as a gravitational waves were detected years ago. But there exists some puzzles in general in the framework of general relativity, like dark energy and dark matter and so on. So there is a resolution. Some people, have been studying is that they consider the modified gravity. That means there is a question that could general relativity be modified, or should general relativity be modified? So if we assume so, that we can modify the Einstein gravity, another natural question is that how far can the modified gravity be away from Einstein theory? So we can think of this question from experiments, of course. I believe I'm not very familiar with the experimental observation or exploration about the gravitational waves and the modified gravity, but I believe it must be ongoing work, and it really requires a very high precision for probing very short distance. And in addition to experiments, we might think about theoretical prediction. Like if we have assumptions, some minimal assumption, a natural assumption, what can we do to say something about the modifications of Einstein gravity? And this point two is basically the one that we would like to discuss today. And of course, if we combine the first point and the second point in the future, that this kind of thing should shed light on a question that a very natural question is that, can signal move faster than light? I will give you the idea later. So our goal is that, according to our understanding of causality, we aim to put bounds on modifications to general relativity and no energy. And we actually understand, well, I believe there exists different understanding, but we understand the modifications of Einstein gravity as a sort of a no energy effective field theory of gravity. That means we consider the Einstein-Hilbert action plus a bunch of polynomials of Riemann tensors, just like this effective action here. We have Einstein gravity and we have a polynomials in Riemann tensors and some matter fields, probably. And this is actually a no energy expansion in terms of the energy over the mass, where the mass m is pretty heavy. Actually, this m is interpreted as the scale of Liouville physics can appear, and and in other words, it represents the mass for higher spin states that is basically hidden from a low energy world. And we have some minimal assumptions. First, we consider the weakly coupled gravity. That means this mass gap m here, although it is pretty heavy, it's still very, very small compared to the Planck mass. So that means we consider gm squared is pretty small, and that means in this work, we actually ignore any loop effects. So here's the plot that I think can show how this understanding works. So the energy goes up, and from here is basically where we're living, and here is the graviton, and maybe a little bit upward is the electroweak scale, and a little bit upward is the Kluskine modes. Maybe, I mean, it might live here, and then here's the new physics appear, which is the higher spin states. And then here's a Planck mass. We assume this gap is pretty large to ensure that there's no any loop effects. And here is the EFT remain, and starting from M, we call this UV part, and this is actually the part that we know very few about them. Are there any questions? I hope I didn't move so fast.
Why you don't include in Riemann square 10? Oh,
yeah, so because it's in 4 dimensions. So any Riemann squared can be, I mean, it can be transformed into Gauss-Balart term by Fourier deflation that is purely topological in 4 dimensions. So we didn't.
But the Gauss-Balart only some particular combination of this Ricci square.
Yeah. Yeah,
but you only have Riemann square 10, it cannot be a topological 10, so you should have some effect.
Yeah, so yeah, I'm gonna explain this maybe actually just later, but okay. I can briefly give you some idea. Is that because we consider weakly coupled, especially for this coupling here is pretty small, so it means that we are now to take the Fourier deflation without altering any physics. If we don't consider like some sort of long perturbative thing like black hole and so on. So in that case, we can take a Fourier deflation, and Fourier deflation can take the Riemann squared to Gauss-Balart compilation, which is topological. So the basic idea is that if you calculate, well, the starting point is that we look into the amplitude. So if you look at the amplitude, there's low ending contribution for tree-level amplitudes from the Riemann squared.
Okay, yeah, please go
ahead. I have a question as well.
Yeah.
So you've mentioned that you're only considering loops above M, right? But below M, you can have in 4 dimensions, like infrared loop corrections, for example. So, so what happens to those kinds of terms?
Yeah, so we ignore loop, and there is indeed IR divergence that I'm gonna actually show you later in our bounds. We didn't remove IR divergence in our bounds, but it makes sense to keep that IR cutoff. But it's an open question that we don't really resolve, that to remove the IR divergence.
Okay. Okay, thank you.
Thanks. So let me give a brief introduction of EFT. So basically, the Wilson coefficient, that is the coupling of the higher derivative terms, characterize the EFT space. And the EFT dimensional analysis suggests that, for example, the Wilson coefficient GI should be some dimensionless quantity GI tutor over you know, the cracked scaling of heavy mass M. But the question is then, how large is this dimensionless coupling, dimensionless quantity? In gravitational theory, we actually have 2 options. The first option is that this dimensionless quantity is actually always order 1. This is usually happen in usual EFT without gravity, and it basically means that the higher derivative terms can never be strongly coupled because this thing is always suppressed if you take the M to be large. And the second option is especially, it's special in gravitational theory because this dimensionless quantity could be in the order that m squared times g Newton times the Newton constant. And that means it cannot exceed the strength of a tree-level graviton because it's surpassed by G Newton. Which one is correct? We don't know. There is some guess. You can make some assumption and derive further, but we don't make assumption and we don't guess. We actually, using our approach, we can actually prove the theorem about how GI should be. This is a sort of a important point. Yeah, so perturbatively higher derivative terms are actually ambiguous because we can always do the Fourier derivation to transform one curvature invariant to another curvature invariant. This is called the Fourier deflation, and it doesn't alter the physics at all. But we have an ambiguous quantity at perturbative level, that is a scattering amplitude. Like in gravitational theory, we can consider this sort of 3 different diagrams. First is the graviton, a 2-to-2 graviton scattering, exchange graviton. And this is the contact contribution that is contributed by the higher derivative terms. And also we could also consider some line matters in the exchange channel. So in this presentation, let's just focus on the MHV amplitude. That is a maximum, I think it's maximal helicity violating amplitude. But in our paper, we actually can extend beyond MHV amplitude. So MHV means that we have 2 plus helicity and 2 minus helicity. So we consider this sort of amplitude, of course, with the crossing. So this amplitude, we can factorize out the helicity dependence and focus on the function, the function of a Mandelstam variable, and this is a crossing condition. So the Lorentz EF expansion for this amplitude looks like this. So this term is contributed by the Einstein gravity, and this term is contributed by the Riemann cube, and this is contributed by Riemann to the 4th, and G5 is this means d squared acting on the Riemann to the 4th. That means we act 2 more derivatives, and this is 4 more derivatives, and so on and so on. And we can also add some matter, but we ignore loops.
So, like, what is when you are taking this low energy EFT expansion, you are just taking that the expansion parameter is E by M.
Sorry, sorry. Can
when you are considering this low energy EFT expansion, that time your parameter is just capital E by capital M.
Capital E over capital M. Yeah. It basically means we expand in terms of the E over the energy over the mass gap. Yeah, it works at that region.
Okay.
Yeah.
Can I ask a question about F matter?
Sure.
So I guess this is coming to another infrared question, but so do you allow higher derivative corrections in F matter?
Higher derivative
corrections in F matter. So let's say you're taking gravity and a scalar field.
Yeah.
So F matter is allowed to have these higher derivative corrections of phi?
Yes.
Okay. And I mean, the reason why I'm asking this is essentially you can have like non-local gravitational theories, which can be recast as higher derivative phi is interacting with the graviton. And so does that constitute some kind of an infrared correction? I'm not talking about the viability as of right now, but I mean, that could provide an interesting structure in F matter, which I mean, I just wanted to know if that's been accounted for in generality.
Yeah. So yeah, thanks for the question. I mean, the F matter here is, we can have the higher derivative terms from matter fields, but it's all considered in this diagram, and and we consider its spin is less than 2, and for scalar scattering, for scalar exchange, this thing is actually pretty, I mean, unique. I'm not sure.
So what do you mean by standard exchange?
Yeah, so that
quadratic and phi sort of terms, like just del phi, those kinds of pieces.
Yeah, so this means so basically we still consider the graviton scattering. That means the external particle is graviton. The matter here basically means that some matter could be interacting with graviton, and it only appears in the middle.
Okay, so it has to be spin 0 then.
It could be spin 0, and it could be spin 1, could be spin 2, but we don't consider it exceeds spin 2, because spin 2 higher than spin 2, in our understanding, it should be some sort of a loop physics in the heavy part rather than the EFT. And of course, you can consider some sort of a higher spin gravitational theory, but I'm really not sure it's what we consider. I think it's not what we are considering here.
Okay, thank you.
And
yeah,
by the way, you do the theory definition, you may change the canonical interaction of the matter with the gravity, right? So after theory definition, the interacting between the matter field may not be in the canonical kinetic term, right? Would this affect the overall form of this amplitude? Or you need to fix it's always canonical after do some theory definition on gravity side?
Yeah. The connected term is always fixed to be the usual law.
Then, okay. Yeah, so you only do the theory definition on the gravity side, but at the same time, you also need to fix the matter field kinetic term to be.
Yeah, we can actually do theory definition for all existing fields. Okay. But the only thing matter for graviton scattering is that we only need to consider this sort of amplitude. And what you mean is that I think, yeah, so we can, if we consider the scalar scattering, we can also look into the specific, the full set of scalar action, and to look at the theory definition and the amplitude for scalar scattering and so on. But here, the scalar thing and the matter thing all appear in the middle channel. That means we only need to consider the vertex in the Lagrange.
If this part will affect your causality consideration later on?
Sorry?
If this matter part will affect your causality consideration later on or not?
Yeah.
Okay, I see.
Yeah.
Okay, yeah, go ahead. Sorry, thank you.
Yeah, thanks. So yeah, let me explain a bit. So what I said before is what we do for what our understanding of modification, or the modification we consider. But there must exist different modifications of Einstein gravity that we actually don't bound. We don't bound in this work. Like FR gravity and FT gravity and so on. It's sort of like equivalent to gravity theory plus additional matter, maybe with non-trivial potential. This is the thing that we don't bound. And also something like the quasi-topological gravity, it's a sort of a thing that the modification are balanced to cancel each other in particular background. Sorry, I should say the background rather than the vacuum. And there must exist many more modified gravities that we don't consider. But yeah. Yeah, if there's no further question, I will move to the next part. Yeah, thanks. So let's review a little bit on what we mean by causality and unitarity bounds. So basically the idea, well, actually the idea comes back to last century, but recently, well, it's not recently, but like 10 years ago, there's a paper showed that the wrong sign could actually lead to superluminal signal. And a toy model is that we can consider sort of an action EFT, like it's a scalar EFT, it's a scalar connected term, and we only consider one particular higher derivative correction. I mean, this paper considered this sort of model. So if we consider the actions propagating on particular background, the background that I denote as phi bar, the background is that the derivative of the background is the constant vector. Then if we do so, the authors find that it is possible for the fluctuation of the scalar field to travel outside of its own light cone if we have a wrong sign of this coupling constant, this Wilson coefficient G. So that is that we can write effective light cone for the perturbation of scalar. That is this thing, and this thing is positive definite, and this thing is negative. So if G, if G is negative, there is a chance for this thing to go outside of the light cone. To make sure it can never go outside the light cone, it's always be causal. We have to require that G is positive. So this is a very naive example about the causality puts a bounce on the Wilson coefficient. But this story can be made more rigorous. That is the dispersive bounce. And there's a lot of papers about this story. But the key idea is that we can start with the low energy amplitude, and we write the low energy amplitude in terms of sum of positive UV on loans. So yeah, and we have two ingredients. First ingredient is the causality, and in terms of amplitude, the causality means that we have a latticity on upper half plane of energy. And for unitarity, that means the probability must sum to be 1. And this has a very important implication for amplitude. That means if we expand the amplitude according to the angular momentum conservation, that is the partial wave expansion, we can actually have a positive and bounded spectral density. That means the imaginary parts of amplitude can be expanded in terms of partial waves. This Pj is a partial wave, which is actually Legends of polynomials. And its coefficient, we call it the spectral density. This guy must be positive and also must be bounded from above. So this is unitarity tells us. And we also laid additional assumption that is Raj boundaryless. That means the that's about the high energy behavior of the amplitude, means the amplitude over S squared at where S is the energy, at very high energy, it should be 0. And that means it's the case fast enough and high energy. But this is actually not what we assume. But this is basically the old story. So if we use this thing, we can write down the dispersive sum rule. That means we can write the amplitude over S times S plus T. And this thing in infinity arc is 0 because this whole thing goes to 0. So we start with the contour integral over along the infinity arc, the arc and the infinity. And this integral should be 0. And then we can deform the contour to be this contour. And here is basically the low energy part, that is the EFT part that we trust. And from here we have some branch cuts. Basically, the branch cuts appear because the Liu physics appear here. That is, we have this is basically the scale that the heavy mass m. So this sum rule can be decomposed into two parts. First, the low energy part, that is EFT. Second, the integral over the branch cuts and the UV. And if we consider the toy model, the action model, the low energy part gives us the minus 2g. And the high energy part gives us something that is positive. So that means we basically, sorry, there should be a minus sign here. I give some, I have some typo. So this gives combine this low energy and high energy together. We have a conclusion that the G must be positive, positive or zero. So they basically reproduce this bond. And this is the rigorous story. And are there any questions? I mean, it's a bit, it's pretty important to move on.
So here,
Go
sorry,
ahead.
sorry.
Yeah.
Yeah.
Apitam, go
So
ahead. Sorry.
Yeah. So fast, you have considered a high energy limit, or like the fast loop diagram is representing a.
Yeah. So for high energy behavior, we don't actually, I mean, we don't actually think of any loops or anything like that. We only assume it must obey this behavior.
Yeah. So
Even,
yeah. Yeah, here also I did not understand that. I understand that why rho j has to be greater than 0, but why it is bounded by 2, I missed that part. Why it has to be less than equal to 2?
I mean, I didn't provide proof here, but the basic idea is that you can use like something like the optical theorem and to recombine rho j, and you will find the very straightforward thing is that it must be positive, but after some calculations, you will find it also has to be upper bounded. But I didn't cover it here. But
Okay.
maybe I can give you some proofs later. Maybe I think there is some proofs in the literature.
Okay. Sure. Yeah.
So
And here, when you are, sorry.
I just want to know
when,
the dispersive sum rule, what the sum rule means. Yeah. What
So,
the B2? What is a relative? What this sum rule means? Yeah, physically. Yeah.
Yeah. The physically it means that. Yeah. Sorry. Actually, I have some typo here, so it might makes it a little bit not too. But yeah. Sorry. Let me expand. So the physics of this sum rule means that we can actually collect IR and UV.
Mm-hmm.
So it means that we can write down some formula that collects IR and UV. That means the IR thing can be written in terms of the sum over some UV spectrum.
Mm-hmm.
So it's basically what it means.
I see. So it's like so it's based on unitarity and or something to get this sum rule, so that the UV and IR excitation are related to each other in some sense.
So according to, if we assume causality, unitarity at all scales,
okay,
that means, and also some Raj boundedness, and that means the key point is that at all scales. So that means something actually applies both to IR and UV. So something must be collecting.
So it's
IR
something like a chroma-chronic relation in the.
Yes, exactly. That.
Okay.
Yeah.
But this is for the
actually
relativity theory. Okay.
Yeah.
Okay. Thanks. Yeah.
Can I ask something? So those PJs which you had, which were Legendre polynomials, if you like naively expand them, don't you get things which have positive and negative signs as well? Like rho is positive definite, I agree with that. But PJs, when you expand them, they're not all positive definite.
Yeah, definitely. Yeah. So rho j is.
So what's the argument that that's bounded? I mean, how, is it rigorously shown, or is it something that on a case-by-case basis, like if you try it out, it works?
Yeah, I'm actually gonna briefly introduce how we actually do this. But the old story, not the old story, but the pretty simple way is to take the so-called forward limit. That means we take t goes to 0, so that we can take some series expansion of Pj. And then, as you said, some of it is negative, but some of some of it is positive, but some of it is negative. That doesn't matter because we can always find a sort of a compilation so that it's positive, and this compilation will make the language parts to be recombined into some compilation of Wilson coefficients. So that means we can still get some bounds on a compilation of Wilson coefficients.
Okay,
but
and,
for this,
that has been shown, is what you're saying. Like that combination being positive has been shown, or it's known.
Yeah, it's
in the forward limit.
Yeah, it's must be true. We can always find some positive compilations.
Okay. And another question I had, I mean, this may be a very naive question. I don't know. I mean, the dispersive sum rule, it seems to be breaking your crossing symmetry expression, right? Because it's an integral over S, and you want it to be invariant under S going to U going to S. That the crossing symmetry relation should be there. So
Yeah,
is that true with this dispersive sum rule? I mean,
yes,
naively,
the dispersive sum rule is actually obeying the crossing symmetry. But I might write something not very correct here, some typo here, I think.
okay, because naively it doesn't look like it's so. Is it something that you can check afterwards, or it's like something that can be seen from this expression straight away?
Yeah, so basically we have two. So if at UV you can have integral along this is a U channel, and you can have integral along this is this is S channel, this is U channel. So these two things are actually symmetric under this precision. There should be additional one over S. I'm sorry, I'm pretty sorry about that.
Okay, yeah, from the diagram I agree, there's nothing that is pretty symmetric, but I mean the integral didn't appear to be so, but I'm guessing it is. So yeah, okay.
Yeah.
Okay, thank you. Yeah.
So, but we still actually have some subversion of causality that is crossing symmetry. So that means if we consider the average value of a commutator of two scalar fields or any other fields, but some fundamental fields in quantum field theory for space like distance, it must be zero. And this is the idea of causality, and it actually gives us the crossing symmetry. So it's actually related to the existence of antiparticles, because if you look at, if we don't have a commutator here, it is not zero, even though it's a space-like. It's the distance is space-like. So we must have to assume we must have antiparticles to cancel. And but it's pretty hard to make it like a theorem. Like why it's because, I mean, this thing should be true, but if we want to translate to the crossing symmetry, we have to do a Fourier transform to momentum space, and this is very hard to prove that it's true. So it's a conjecture, it's assumption that it's true. The causality means crossing symmetry, but it's really hard to make it like a theorem. Many people have been making efforts toward this, but it's hard. But it is actually rigorous in ADS-CFT, because CFT has a pretty rigorous axioms to ensure that this is true. So we can start with the ADS-CFT, and we take the flat space limit of ADS, and that convinces us this must be true. And this work is done by Karen Holt, Mazak, Restani, and Simstoffen, like last year. So the subproportional causality means the crossing symmetry. And if we use the crossing symmetry, like just like asked before, that this thing may not be very obviously obeying crossing symmetry, but if we really impose the crossing symmetry, or really not impose, I mean, how to say, the crossing symmetry is there. If we if we think carefully about quotient symmetry, there will be some consequence. A good consequence is that we can have two-sided bounds of EFT Wilson coefficient. This is pretty important, and it's also done like years ago, like 1 or 2 years ago. Yeah, please.
Yeah, I'm sorry. Maybe I should have asked this long back, and I'm really sorry if this is very silly, but when we're talking about light cone and space like separated and all these other things in the present context of like a gravitational theory, do you have in mind an expansion about flat space or about a particular background? Is this important in any way?
Yeah. This is what we're gonna introduce later. It's not, yeah. So far we're all considering. So far I'm all reviewing the usual quantum field theory without gravity. So
okay.
It should be no any ambiguity here to define light cone.
Okay, thank you.
Yeah. So what we mean by two-sided bounds is that, for example, here we only have a G is positive, but using quotient symmetry, we might get something like G is larger than 0, and it's also smaller than some value, some numerical value over the correct scaling of heavy mass. Yeah, let's move to the gravity story. Sorry. So the story with gravity, it's true that it is very subtle, since there's really no globally well-defined light cone in non-trivial backgrounds. But we have a resolution is that one thing is that we can measure at asymptotic infinity for asymptotic flat space. That is what we consider actually, because we consider the graviton propagating on the Minkowski space. That basically means that we consider weakly coupled gravity, and graviton has very small effects to affect the backgrounds, and we measure the causality at asymptotic infinity. And there's a famous paper by Camejo, Destin, Medicina, and Chibodov about, we called it the CMZ bounds, and basically some notion of causality, classical causality. And that is that they measure the time delay of graviton going through gravitational shockwave, and the gravitational shockwave is pretty classical thing. So we call it classical causality. That means if we have a shockwave here, excited by graviton, for example, and we let the graviton go through this shockwave. After go through this shockwave, it develops a time delay. So this is a time delay. And what if we find a time advance, that will violate the causality, because time advance means time delay is negative. That means we go in here, but we go outside from here. That means before we inject a graviton, there is already a graviton going outside from shockwave. So measure the time delay of graviton going through gravitational shockwave, actually equivalent to considering the Icolo scattering for gravitons. That is equivalent to the Icolo phase, which is actually the Fourier transform of amplitudes with respect to the momentum transform. So this Lies dictionary, the negative phase eigenvalues means the time in advance, means the violation of causality, and the formula to calculate the time advance or time delay is you take the derivative for Icolo phase with respect to the energy. And in this case, they find the Icolo phase looks like this. So to ensure that the Icolo phase must be positive, they conclude that this G3, which is the coupling of Riemann cubic, must be bounded from above. Oh,
so that result is in 4 dimensions, right? To get the log.
Yeah. This is 4 dimensions. So we have the IR log here.
Okay, thank you.
So this is just a parametric bound, not sharp and quantitative. The question is, can we make it sharp? And also it is actually insensitive to contacts. That is the derivatives acting on the Riemann to the fourth. Another question is that besides the CMZ argument, can we have actually similar story for dispersive bounce for Graviton? Yes, but the problem is that, as I said, the past, I mean, the technique in the past is that we take the forward limit to expand the energy, both as well as the high energy. That means we take t equals to 0 limit, but t equals to 0 limit is pretty dangerous when gravity exists because of one of the t pole. For example, let me remind you, we have a 1/t pole here. But we can still have some higher subtracted sum rules. That means higher subtracted, that means we can divide by higher power of s times s plus t. If we do that, the energy part will be free of any pole, but that means we can only probe the positive bounce for contacts rather than the real Einstein gravity and the Riemann cube.
So if it goes higher than 1 over s squared, wouldn't that violate the Frossard bound?
No, because the Frossard bound the Frossard bound is something like the Raj bound. It's actually just what we assume by Raj boundness. It means that m goes like at most s squared. As it goes like at most s squared, we can of course divide it by higher and higher power.
Oh yes, you're talking about the. Oh, okay, sorry. Yeah, okay,
yeah.
Got it. Sorry.
It's even more convergent.
Yeah, got it.
Oh, sorry. But for probing the coefficient of 1 over t, the idea is proposed by Karen Holt, Mazak, and collaborators last year. That means we don't take the forward limit. Rather, instead we transform to the impact parameter space. I'm going to introduce it later. But yeah, am I going too slow? I think that I'm always still running out of time.
It's okay. We don't have time limit. Also, we have many questions, so don't worry.
Yeah. Okay. So our assumption, let me move to the causality of gravity. So our assumption first is the causality. We assume the causality, and that means in our case is a relativity plus quotient symmetry. And second, of course, assume unitarity. And in terms of graviton, the unitarity is not just the positive spectral density, it's actually the positive spectral density matrix, because the spectral density is a matrix when you have spin for external particles. And this a bonus is that we don't need to assume Raj boundedness. It can actually be derived from causality and unitarity if we smear the amplitude. This is what our strategy is that we don't actually directly consider the amplitude. Instead, we consider the smeared amplitude. That is the amplitude integrated against a wave function over the transform momentum with compact support. I will briefly sketch the proof why this smeared thing together with causality and unitarity means that the sky must be bounded by linear in S, but this is what we use. But to have this property, we have to take the wave function to have two property. First, the wave function must have finite support in momentum space, in transfer momentum space, momentum transfer space. And the second point is that the wave function must decay fast enough in impact parameter space. I'm sure what it means. So this is the example of a wave function. I didn't show the explicit mathematical formula for the wave function. I just showed the behavior. And this is a momentum space. It starts from p equals 0 and it ends from p equals 1. So that means it's compact port in momentum. And for impact parameter space, this impact parameter space, the wave function actually starting with some value and decays fast enough. Like for impact parameter to be like a 10, it's almost very small. Extremely small. That means it decays fast enough in the impact parameter space. So I'm going to introduce the dispersive sum rule we use. It becomes precise if we smear the amplitude and so smear the sum rule. But now let's just to be easy, let's just look at some sum rules without smearing. So when the amplitude is smeared, the wedge growth looks like this. If we look at the plus minus minus plus amplitude, we have this holistic dependence and the function, and this holistic dependence actually goes like s to the fourth. And so the whole thing, because the whole thing as we derive here, when it's smeared, the whole thing should be less than linear in S. And plus minus minus plus is looks like this. And this holistic dependence goes like linear in S, and the whole thing is less than the linear term S of S. So this thing leads to the wedge growth of the function that we will establish. We will build the dispersive sum rule. So for S, F, S, and minus p squared, this go like S 1 over S to the 3. And this thing goes like linear in S. So what this means? It means that this kind of function is not growing at high energy at all. It actually decays. It's actually decaying at high energy. So this is the example of we call the super convergence. So we don't even need to subtract anything in the sum rule. We can actually multiply something in the sum rule because it's super convergent. Even we multiply something, it's still convergent. So that's really helpful. So and then we can establish the sum rule because the sum rule must be SU symmetric in the crossing according to the crossing symmetry. Like we deform the contour, it must go both S channel and U channel. So it makes life easy to make it crossing symmetric in S and U. So what we do is that we construct SU symmetric compilations with Lie's convergence. So let me just give an example for superconvergent sum rule. This is superconvergent sum rule here. And because if we use this thing plus this thing, it makes sure it's SU symmetric. And of course, this thing is SU symmetric. Oh, is there a question in the chat? Oh, yeah, sorry. And this coefficient here is SU symmetric. And this thing goes to 0 for all even number of k here when k is larger or equal to 2. And this gives this superconvergent sum rule here. So this is just a simple example. And I'm gonna give you some idea about what we mean, our algorithm to bootstrap the bounce. So I call it bootstrap algorithm. So in particular, the sum rule, of course, as I reviewed before, it gives the minus of low energy contribution equals high energy contribution. And the algorithm is that if we are able to find a functional f such that this functional acting on the high energy part is positive definite for all masses and spin j, we then, according to this equation, we can prove that minus of functional action on the low energy part must be positive definite. That gives us some bounds on Wilson coefficient. Yeah. So this is actually, in mathematics, it's actually called the semi-definite programming problem. And we use the software, we use a package called STPB to find optimal F so that we can get the optimal bounce for Wilson coefficient. And STPB is a very nice package that is designed by David Simstoffen. It's pretty cool, and it's commonly used in the community of Bootstrap collaboration, that people use it like to solve the strongly coupled conformal field theory, and also the EFT bounds and S matrix Bootstrap and so on. Our choice of functional takes this form. This is the functional. If it acts on the sum rule, this functional means that we integrate, that we smear the sum rule. That means it means we have a sort of a wave function times the sum rule and integral over the transform momentum in the compact support. And usually, well, in our case, we usually assume the wave function. We usually choose the wave function to have compact support in momentum space and decay fast enough in impact parameter space. But it's also interesting to think of how this sort of approach can reproduce the forward limit bounce. It basically means that we have to consider this wave function to be a linear combination of a bunch of delta function and derivatives of delta function. So if we use this wave function, that means our functional is actually the sum of a linear combination of derivatives, linear combination of expansion around the forward limit. And if we consider the finite p support and fast p decay wave function, that actually resolves graviton pole problem in higher dimensions. I forgot to cite here, but it's basically done in this paper. It's basically done in this paper. And usually we usually take the wave function to be a polynomial in transform momentum. But in d equals 4, even though we do that, we use the wave function to smear the sum rule, we still get some divergence. It's because of some Newton potential exists in 4 dimensions, right? Newton potential, we have 1 over r, which is actually reflecting the IR divergence of graviton. So our strategy is that we actually just put an IR cutoff here. We put IR cutoff in the integral measure here. And to give you some idea, if we take the mass and spin at UV spectrum to be very large, it actually manifests the impact parameter space, because the impact parameter is basically 2j over m. And if we take this limit for the smeared sum rule, it's equivalent to the same functional acting on the Bessel function, and the Bessel function is basically, and this thing is basically the Fourier transform of a wave function. So it means this limit basically means we are using the impact parameter space for wave function. And now we can briefly sketch the proof for smeared Raj bundleless. So if we have a smeared amplitude and we have a partial wave expansion, so when s goes to infinity, and the Legendre polynomial is basically order 1, and then because the wave function decays fast enough in impact parameter space, and impact parameter is based in 2j over m, that means it effectively cut off at some maximal, at some large spin. That means we can effectively evaluate the whole amplitude below j equals some very high value, some value of b times square root of s. So this whole thing is actually just less than s times the constant. Yeah, are there any questions or?
Yeah, I mean, I can ask it later if that will help, but it's
Yeah,
more
yeah.
about the. Should I ask it now?
Oh yeah, please go ahead.
Yeah, so I'm just a little curious about the smearing procedure. So it looks like uh, you're saying that, okay, so normally you have like this low energy, high energy equivalence for a certain part of the spectrum, right?
Yeah,
And that's what the dispersive sum rule is giving you. And you're
yeah.
saying we're going to smear it now with this function psi, such that it looks like the transfer momentum is bounded within this EFP region between 0 to m. And so I'm guessing the impact parameter here would also naively be something like 1 over m. The impact parameter is bounded by 1 over capital M, right? So what we're doing then is like restricting this high energy behavior to some low energy observables. Is that correct? Like we're not considering the full high energy spectrum, we're putting a cap on the high energy spectrum by smearing. Would this be an accurate description of what we're doing?
No, I don't think so. I'm sorry, but I think that the smearing procedure is that we put the compact support in P because that's how we want to make our bounds, but it actually doesn't have any effects on UV. That UV is still UV, but we just mirror the UV.
Right. So it's like you're truncating the IR part, the IR divergences that you could have from this. Right.
Yeah, if we truncate the IR divergence, that means we must restrict the UV to below some very high impact parameter. That's true.
Okay. And the second point is this relation which you have on 20. So in 4 dimensions, by introducing this MIR, are you putting a large impact parameter cutoff as well? Because from the looks of it, there was originally just a small impact parameter cutoff, but now you're putting a large impact parameter cutoff as well, right?
Yeah.
Like you're not allowing it to go to arbitrary large values.
Yes, we're not allowing the impact parameter to be very, very large, as I will show you later, because if we put a cutoff, if we put the IR cutoff, actually what we found that positive functional cannot be always positive. It will go to negative if we go to very, very high impact parameter.
Okay. And okay, so you can get negative if you take large impact parameter. Okay, that's kind of interesting. I mean, when it comes there, I'll probably ask again.
Yeah.
And this last point I wanted to know is about this forward limit condition that you're talking about here. This delta 2k going like in the limit of talking about derivatives, you recover a forward limit bound. I mean, I didn't quite get that.
Yeah, because if you insert this thing into this formula, and basically you can integrate this over because of a delta function, and if it's just a delta function, you take p equals 0, and if it's a derivative of delta function, you can integrate by parts to move the derivatives on the sum rule, and then you take the p goes to 0. So it kind of equivalent.
Okay, so you first. Okay, so you're saying first evaluate the delta function, which basically picks out it's saying that it has support within this region, and then you take p going to 0, which is to say that you're working within this regime of 0 to m actually.
Yeah.
Okay, I think I got it. Okay, thank
you. Yeah, thanks.
I want to know what the smearing, you are considered causality problem, right? And then why you need to do the smearing, I still why this is essential, yeah.
So the issue is that why we do smearing is because so basically it's because we want to resolve the Graviton pole. So in the sum rule, if you in the low line sum rule, you will have a 1 over t. So this thing makes it not possible to take the forward limit.
So my I just want to get a physical picture. So for example, if we talk about causality in the particle picture, so in some sense we have the light cone, and then if we have a well-defined pole, then it's we have the particle picture. So we can say, okay, if this particle moving with a speed of light larger than speed of light or not, right?
Yeah.
But if we have a branch cut, then the particle picture is blurring. Then I have more difficulty to understand naively, especially I want to have a classical sense. Then for the excitation without a well-defined particle, then in some sense this kind of argument will be more vague, right? So I'm not so sure if this smelling is the way to fix this kind of vague picture. So in some sense you smell out that part which don't have something like a free particle behavior. So it's very hard to say if this is valid causality or not, and you only concentrate with the one which you can have more physical particle picture. We can talk about causality. If this physical is a motivation.
Yeah. So may I put in this way? So by causality, what we mean is that the amplitude is analytic at the upper half plane of energy, and it is quasi-symmetric. How this is related to the very clear physics picture is that we don't really understand how to prove. But some toy model and some successful story without gravity means that this should be the correct story. So we actually pretty conservative that we are not saying that our understanding of causality that translate the causality to the analyticity and causal symmetry must be correct. But the idea is that if we understand causality like this, we get something, and this thing must be true if our understanding of causality is correct. So we can let the future experiment test if this understanding is correct or not.
Okay.
So this is our idea.
So in some sense, still based on analyticity, and this measuring procedure is just fix some for example, IR pathology, you don't know how to deal with when you.
Yeah.
Okay.
Yeah.
Okay.
Yes. Yeah.
Thanks. Yeah.
So I move to the cassette. It's still cassette of gravity. I'm sorry. Sorry, it's something's called me. I have to cut it down.
No problem.
Yeah, so we have some example bounds. Let me just briefly review some example bounds from forward limit. So the idea is that for forward limit, we can only use the higher spin sum rule and thus only probe the contact. And there's exists some positive bounds years ago by a bunch of people. So for example, if we consider the before sum rule and relate energy to high energy, and it writes the G4, which is the coefficient Riemann to the fourth, in terms of positive things, and this must be positive. So this is an example bound. And if we use quasi-symmetry, this actually makes it actually makes the same coupling appearing in different sum rules. So we get some so-called the non-constraint. This is investigated by these people. So for example, if we consider G6 prime, this is basically the coupling from D to the fourth acting on Riemann to the fourth. It can be written by this average, and we actually have the same thing. That means we have a G6 prime equals something else. So, but G6 prime must be the same. So we can take a difference, and that means we have something to be zero. we have some heavy average to be 0. So this thing is called the long constraint. Using the long constraint, one can actually derive the two-sided bound. And this is an example from this paper by Born, Kosmoskos, Chibodov. And it gives a bound that G6 must be positive, of course, and it has a two-sided bound for G6 prime over G6. And this thing is actually understood by analytic approximation at forward limit. That means they actually don't use SDPP to do numerical stuff. They use analytic procedure to derive the same bounds. And this tool is called the EFT hadron, was first proposed by Cunningham Lima and Yuting Huang, and later by developed by some other people. But they actually found a very interesting thing is that they consider a specific model and to see what their value at low energy lives. So this is the bound, the EFT bound, the Causality bound live. It goes from minus slightly over 11 to 6. But all known, all this known theories actually is rather smaller than the allowed region. So they want to shrink the bounds to close to the theory island. For example, it's very obvious that G6 prime must be actually also positive. They can do this if they assume additional assumption that's a low spin dominance assumption. That means they assume the spectral density at high spin is smaller than the spectral density and low spin.
Can you please clarify what this graph really is? I mean, I'm not quite getting it. So it says A21 over A20. And what do you mean by G6 in these other theories?
Oh, sorry, this is a different convention. I forgot to mention. This A21 is G6 prime in A21 in their paper is G6 prime in our paper. And A20 in their paper is G6 in our paper.
And what is G6 in the context of these other theories, like fermion vector, Rarita-Schwinger? What do you mean by that? Where the external particles are, instead of gravitons, you have it as these other particles? Is that what you mean?
Let me give you the idea here right now. I may actually plan to introduce later. So what they actually consider is that they consider some loop effects. So you scatter gravity, but you consider some matter fields circling around the loop. For example, we have this box integral, and they consider that this loop here could be spin 2, spin 3 over 2, spin 1, spin half, and spin 0. That's basically what they mean by the model, like the spin 2 model or scalar model and so on. So this is the loop level. So if you integrate out the loop effects, and that can give you some tree level of EFT. So this thing can be effectively described by a context with particular Wilson coefficient.
Yeah, okay, I think that's clear. Thank you.
Yeah. Yeah. So I'm gonna move to the Liu results. That is that the gravity is special. That I actually mentioned before, we have superconvergence sum rule. So let me consider the low line sum rule, that is superconvergent one. This one is it's very beneficial because it contains low energy context and low energy. It only just gravity, the Einstein gravity and Riemann cube. So let me give you some simple warm up. That is, we can actually easily find a positive functional such that it acting on the heavy stuff is positive definite, but it acts on the low energy, has some effects that it acts on the p squared. Sorry, it's a typo. It acts on the 1 over p squared. It acts on the 1 over p squared is 1, but it acts on the p to the 6 is 0. So that means we prove a bound that G Newton must be positive, And also it must be bounded from above by 1 over m squared. So that has two implications. First, we actually, from this functional, we actually prove gravity is attractive. We don't need to assume that gravity is attractive. We prove that G Newton must be positive. And also we verify that gravity is indeed weakly coupled as we assume, because gravity is, the G Newton is bounded from above by 1 over m to 1 over m squared. That means 1 over m Planck squared is less than 1 over m squared. That means m Planck is much, it must be greater than the heavy mass m. So this is the warm-up. But we have to be in caution. We have price of IR cutoff because we put the IR cutoff. So the price of IR cutoff is that our functional, although it's basically negative, it's basically positive everywhere, but it goes to negative at very large impact parameter. How large? It basically is the IR cutoff to the -2 over 3. So this is an idea that if we take if we transform to the impact parameter space, then this is basically the usual functional goes. It decays fast enough in impact parameter space and just stays very small along impact parameter until it goes to very, very large. Like if we take the cutoff to be 10 to the -6, it will goes to like 100 times 1,000, like something. Sorry, 10 times 1,000, something like that. At this point, it goes to negative. So we have to keep our impact parameter to below this very large impact parameter. So natural question is that, can we control this negativity? If we can control this negativity, we might get some stronger bounds that can move the IR cutoff to some UV parameter, but we don't know. This is what we actually tried very hard, but we really didn't make it in our paper. Maybe we can keep pushing in the near future, but we don't know the answer yet. Maybe the dress-up amplitude would be a solution. We don't know.
Do you suspect that this can be resolved entirely at the level of tree-level amplitudes?
Sorry?
Do you expect this to be resolved within the level of tree-level amplitudes, like without considering loop effects, IR loop effects?
Yeah, we don't actually expect that. So to resolve this, we must consider, I mean, for very large impact parameter that the negativity could appear. If we want to resolve this region, we have to go to something like the I-color region. So if we go to the I-color region, that means loops will be packaged together to give you the I-color scattering. So there must be some loop effects that we have to consider, I think, if we want to resolve the IR divergence, but we don't know how to do. So at tree level, if we want to resolve it at tree level stage, it might be possible, but I think we must start with some IR safe observable, like the for example the dressed amplitude or something similar. We don't know. Yeah.
Okay. Okay. So I'm not quite sure what you mean by the finite observables in the context that you're speaking about here. But what I was thinking along the lines of is the non-analytic pieces that you've written for the tree level. Mm-hmm. If you took IR loops, you'd end up with a log t sort of term, for example.
Yeah. Yes.
Now if you take t going to 0 there, and we can't comment on the sign a priori. So of course, this will probably involve some modification of your smearing function. But you can imagine a scenario in which this 1 over t from the graviton pole somehow cancels with this log t in the loop, and this has some precedent, I guess, in the literature, which is the way the soft theorems, the way in which IR divergences cancel in field theory normally, which is like virtual soft particles cancel out with real soft particles. So like the soft limit of the pole would cancel out with these loop effects. So that's what I was thinking along the lines of.
I see. Yeah. I'm not
so
sure.
A log t squared would cancel out with a 1/t in the graviton pole.
Yeah, I see what you mean. Yeah, but what we want to do is that we don't really want to consider the loop effects at low energy.
So you're saying that you're saying that the positivity here would arise in a different manner than it does in the standard field theory calculations.
Yeah.
But like we also know a couple of other things, which is like the IR behavior of like gravitational theories is sort of universal. So it may be that the mechanism is also kind of universal for these leading order divergences, right?
Yeah.
Like the UV behavior is specific, I guess, to the kinds of higher derivative terms that you have. But the IR behavior might be might have some universal way in which they cancel.
Yes, that's how we tried. We want to cancel the IR by using the Icolo limit that actually package up the loop.
Okay.
But we actually fail. But I'm really not sure if we consider not that we consider the real loop low energy rather than the Icolo stuff can resolve this thing. I'm not sure, but
I think they are equivalent in some way. They are equivalent at the end of the
they're okay. Yeah, I think so. Yeah,
it's just the way that we describe them are different. And in impact parameter space, I guess the iconal approach is the best way to go. Like in terms of these impact parameter Fourier transforms, and I mean the iconal approach, similar to what Veneziano and collaborators are doing, I guess, is the way to go.
Yeah. We tried. We try to like something like, let's see, let's trust the Icolo approximation at pretty high impact parameter, and then let's see how if it can cancel the 1/t pole. But the result is that I mean, it has two parts. The first part indeed cancel the 1/t thing, but another part is that it recreate the log part.
Oh, I see. So there's something residual at the end of the day.
Yeah. So maybe, but we might do something not very appropriate. I'm not sure. We still don't have much insights about how to resolve the IR divergence, but we can discuss it later if you're interested.
Sure. I mean, that's kind of like what we are looking into here. I mean, not in this context, but at least in the case of black hole scattering.
The point I think the IR divergence program may not be whole for the higher derivative term. Yeah.
But here it's being spoken about at the level of amplitudes, like just general amplitudes.
Yeah, but it's including the higher order correction, like the G4, G6 correction, right? And the usual program is people only check for Einstein gravity, I think. Yeah, so I think there's the possibility this Icolo type of cancellation may not be true.
So sorry. Actually, the log here appears from Einstein part, because if you probe the whole thing, like you want to bound the contacts, and it says contacts must be elective than something times Einstein gravity. So the Einstein gravity comes with the log.
So if you go to the higher derivative, the log IR divergence would not appear. Is what you mean?
Yeah, the IR divergence is not in the higher derivative one, but we want to bound the higher derivative one in terms of Einstein gravity. That's how the IR divergence appears.
But if this is the case, then maybe like Colin suggests, usually the I think the loop correction, the so-called loop, it means also like a low energy loop because it's the onshore loop. It's a soft graviton in the loop. So it's also still in the low energy region, but this way cancel the log divergence in the aconal scattering.
Mhm.
Yeah.
Yeah.
This is usually in the Weinberg they show this would be the cancellation.
Yeah.
Yeah.
Yeah. Yeah.
Yeah, of course, people didn't discuss a lot on S matrix, so on amplitude. So, but this should be the case. Yeah.
Yeah. It could cancel something, but maybe because of some particular procedure when you are trying to find a bounce. But the point is that the UV thing can reproduce in log. I mean, just as I said, it cancels one IR divergence and it creates another IR divergence.
I see.
Yeah. I'm not, yeah.
Okay, just
Maybe
two
we can
short.
discuss. Yeah, go
sorry.
ahead. Yeah.
Yeah, just two short just to clarify what you just said. So you mean to say that this log T thing, this residual thing that you're getting is coming from a UV loop or something like that? That you just said? Like you said like the cancellation is not exact and there's something left over.
So no, not really, because we're not really looking into the amplitude itself. We are looking into the sum rule. So there's no and according to our procedure, there's no adding 1 over t or log t or anything like that.
I see. Okay.
What we have is log IR divergence.
Okay. I got you.
Yeah.
Okay. And when you said dressing earlier, you meant iconal, like the iconal dressing of e to the power like a0 by a1, like the one loop dressing that you would normally have in the iconal case. Is this what you mean?
Yeah, I'm really not sure, because I'm really not sure about the dressing thing, but I've only heard about that it might be possible to address the IR divergence, so I'm not sure.
Okay, but you didn't mean something like Faddeev-Kulish kind of dressings, or you did mean that?
I don't think so. Yeah.
Okay, fine. Thank you.
Yeah. So we can actually reproduce the CMZ. That the idea is that we can write down the matrix sum rule at some limit of our sum rule, and then at no energy part it gives 2s times the icolor phase, and at the high energy it must be positive. So this proves the thing that from CMZ argument. But the CMZ is built into sum rules. That means, so this trying means that CMZ is built into sum rule rather than just argument like the measuring the shockwave time delay and so on. But also the CMZ requires that the impact parameter must be much larger than 1 over m. And this is actually just a part of our assumption that we consider capacitor P is less than m. But we actually have a different assumption from CMZ. CMZ assume that GS is pretty large, so that means they live in a classical regime. But our regime is the weakly couple, that is GS is much smaller than 1. That means different regime actually labels sharp bounce. Like CMZ is not sharp bounce, but if we stay in a different regime, like the weakly couple regime, we actually can have some sharp bounce rather than parametric bounce. So let me give you some new results with our plots. So like this is some optimum bounce involving G3 and G4, where G3 is coupling of Riemann to the cube, G4 is coupling of the Riemann to the fourth, and this is the plots. And this blue region is the region that the Wilson coefficient allowed to live with allowing line matters. And this I should say is yellow or orange, but never mind. This yellow region is the allow region without allowing line matter. It's just a comparison. But the idea is that you can see, although allowing line matter make the plot a little bit bigger, like make the region a little bit wider, but it doesn't really narrow down. It doesn't really narrow down the cutoff M. So it means that allowing net matter with the spin 2 or less doesn't really narrow down the cutoff M. So it means M is really a higher spin mass. This is a bonus from this bounce. And also, now the dashed tangent is actually just a forward limit bounce. And also, from this example, we can see we actually prove that G3 goes like 1 over M to the 4th, and G4 goes like G over M to the 6th. We don't do any guess. We don't make any assumption about the scanning, but we just derive the scanning from minimal assumption of causality, unitarity, and so on.
Is there any significance to the island width that you have? Like you found out that it's like lying up to this 12 or whatever in these units. So is there any significance to the bound that you have there?
Yeah, the significance is that it means that the higher derivative corrections cannot be arbitrary. It cannot be arbitrary. The Wilson coefficient must be bounded in terms of the gravity. So it means we cannot, if our understanding of causality is correct, it means that we cannot have a no energy effective field theory of gravity with Wilson coefficient beyond this region that has UV completion. So basically something like the Swampland story.
Yeah, I mean, what I was getting at is like CEM said, they just determine that it's parametrically like you could say like 1 over M to the 4 or whatever.
Yeah.
Whereas here you have this specific window.
Yes. Yeah.
And
so that means
I was wondering if this window has any connections to like any implications on G2 ultimately, because you can go down the hierarchy, you can go down in the scheme, right? So this is G3, G4, and it can tell you something about like the parameters which are higher up and lower down as well. So like, can you reduce it finally? Is it just entirely in terms of just capital M, or does it have any sensitivity to the IR cutoff as well and other things?
What do you mean? I'm sorry, I don't understand.
So you've written this. So this plot takes into account the UV cutoff M, and IR cutoff MIR, and the Newton's constant. So does it depend on all of these to get that kind of parametric plot? This kind of bounded parametric plot that you have. Like, is there some specific dependence on these parameters, which gets you these?
No.
Okay.
No. Yeah.
It's nothing like that.
The number here is very, it's very robust.
Okay. Thank you.
I have just a question. So if you consider, for example, the charge matter, do you think this way reproduce some kind of higher derivative analog of the weak gravity conjecture?
Yeah, that's what we want to do. But
the matter you consider now didn't carry other the
we can consider like the two scattering graviton and photon, the mixed coordinator, and that probably can say something about weak gravity conjecture. I know something. Yeah, I know someone must be doing similar thing.
Okay.
But we haven't moved that fast. We are actually currently focusing on higher dimensional extension of this story.
Okay, I see. Maybe Chris Chung have something. They consider.
Yeah, they have some. Yeah, they have something. But what we find is actually, so they make additional assumption about the scaling Wilson coefficient.
Yeah. they have some argument for weak gravity conjecture on higher gravity, and then they constrain on this Wilson coefficient. But
Yes.
you are start from more elementary property,
Yeah.
right? So
Yeah,
that
yeah,
would be related.
Yeah. This is definitely an interesting, important question. So yeah, this is just more bounds. I'm sorry, I'm running out of time, so I just show you some plots. But I'd like to still mention a little bit on this thing. This is G6 prime versus G6. And G6 and G6 prime is all just two coupling for D to the fourth action on Riemann to the fourth. And from this plot, that means if we really include the Einstein gravity, this actually very surprisingly proved that G6 prime must be positive. So that means we don't need any low span dominance assumption, and we can prove this bound if we include gravity, if we probe the Einstein gravity rather than just using forward limit. And this is our bounds compared to no span dominance. And this last part is just simple part that if we consider it's possible experimental implication. So if we consider we observe some deviation from Einstein gravity, like for example delta R at scale L, and this deviation can be accounted by, for example, by R Riemann to the cube. By this coupling, it basically goes like delta R times L to the fourth. For example, if we consider a sort of a 10 sun mass black hole with size 1/10 to the minus 11 eV, then we basically could account this by G3 goes like this value. So our bound, as you see, our bound means that G3 squared must be negative than something an order one numerical value over m to the 8. So this basically implies the higher spin stage must exist with mass less than for this sort of value much smaller than the 10 to the minus 6. So it means that, however, if we look into the Collider analysis, some paper from LHC, if we trust their analysis, it means that because they didn't find any clue for high spin states, so it means that the m must be very large. It must be large enough. Basically, it must be like larger than MEV. So it's actually in tension with our bounds implication for large scale observation. So the consequence is that if the modification of Einstein gravity at large scale can be observed, it will not be hidden from Collider, unless our understanding of causality is missing some essential ingredients. So let's let experiment test it in the future. We are pretty conservative. Summary. So causality is powerful, and together with modern computing techniques and computational power, we can efficiently bound EFT. We can prove the scaling rather than dimensional analysis. Applying to gravity, we can constrain the modification of Einstein gravity in terms of a Newton constant. And our bound implies that if there's no Einstein-Hilbert action, there will be no any higher derivative ones. And our bonus is that we proved EFT UV parameter M must be the massive higher spin massive high spin states. Then we have some experimental implication is that we actually challenge the long-term notion that large scales can make new physics hidden from Collider manifest. We'll let the experiment test it in the future. And of course, as we discussed so many today, we have so many outlooks like how about the bounds for gravity coupled to matter, like swap plan conjectures, which is weak gravity conjecture, and so on. How about loop effect? How about higher dimensional generalization? And can IR tells us some about UV, like and so on and so on. I'm really running out of time. So sorry. Thanks for your attention.
Yeah, thank you very much. It's sorry, yeah, it's good to have very interesting discussion. Yeah. So any
It's,
more question? Yeah, go ahead. Yeah, sorry.
I mean, it's pretty late for you, so sorry.
Yeah, yeah, it's okay. Yeah, it's a interesting talk. Yeah, very interesting talk. So I think we have enough question, right? Do anyone have one or more question?
Yeah, I think I can I can go for one or more.
Okay, sure.
If it's fine. I mean,
It's okay.
if the speakers has to go, I can. It's fine. I can stop. I
Oh
mean,
yeah, it's my morning. I don't have anything to do, so please go ahead.
Yeah,
please go
I
ahead.
was wondering about the first point itself. I thought that might have been so. So in the earlier swampland paper, I believe there was the effect of gravity with like scalar higher derivative terms were considered, right? And so you're not in this paper. There's no comment being made about how um, higher derivative corrections to Einstein gravity affects this F matter part. That has not been addressed so far.
Sorry, FX what F?
So in the early F matter, like in you had the amplitudes from the
yeah.
higher. So that is not addressed so far, is what you're saying.
Yes.
So you've just commented on just the gravitational part, you could say, of the whole theory.
Yeah, we can couple. We can. So let me put it in this way: we allow light matters. That means we consider gravity coupled to matter, but we didn't really bound the coupling. We just allow them to exist without altering the positivity.
Yeah, and in that paper there was like this interesting effect of the two-sided bounce, right? So what was the equivalent of that in this context for the higher derivative corrections? I mean, I might have. I mean, I noticed that for G6 and G6 prime and those things that you were saying, but they can also go like these relative couplings can also have positive and negative values, is it? Like for all higher orders, like for G6, G8, and so on. Like this two-sided bounce exists to all higher order corrections, or you've checked this only to
it exists for all higher derivative terms, but I'm not entirely sure if all of them have two-sided bounds. Maybe some of them only have one-sided bound. I'm really not sure, but the thing I present here must have two-sided bound. For example, like this thing, if you just look at G6, this part basically means G6 must be larger than 0 and less than this thing, right?
Okay. So everything that lies within that wedge would have a two-sided
bound. Sorry, what?
Everything that lies within that dashed line would have a two-sided bound, is what you're saying. In
the dash, sorry,
like that would exist for all higher order. Like there would be an equivalent of that dashed line for higher order couplings, and you would find that.
Sorry, maybe I said some. So this dashed line is the forward limit for G6 over G6 prime over G6.
Right, and you would find a similar dashed line for higher order corrections.
Yeah, sure.
Okay, sure. And so anything that lies within that would have this two-sided bounce, is what you're saying.
Yeah,
so you expect this to hold. Okay.
Yeah.
And I might have just missed this part about the challenge to experimental physics. So what was that MEV part which was discussed right at the end? This intention, one? Yes.
Oh yeah, I'm sorry. So it basically means if we observe a tiny, even though it's pretty much the tiny deviation from Einstein, even though it's tiny, like 10 to the minus 20. Suppose we observe it. So that if we observe this tiny deviation, if our understanding of causality is correct, and so our bounce is correct, this means we put a bounce on the mass gap M.
I see.
So this means the M must be less than 10 to the minus 6 UV. But if we have that small, I mean, if we have that how to say, that small mass M, it's pretty small, then Collider must be able to find it.
You mentioned the MEV, right? It's not this is 10 to minus 6, not 10 to 6, right?
Yeah.
I mean, in the third item you mentioned M is not enough. It's greater than MEV.
Yeah, I'm having the same confusion.
Yeah.
Oh, sorry. Yeah. What I mean is that if we have, so the Collider allows means that M is, so yeah, maybe this MEV is confusing, but the idea is that the Collider analysis implies that M must be very large, but the deviation of large scale means that M is actually not that large. So yeah, this basically.
Oh, so you mean that this M is kind of the cutoff scale, right? So you mean that the cutoff scale actually is not so large. Usually we think about UV physics cutoff scale may be higher than MEV or EV scale.
Yes. Yeah, because this cutoff must be large because we didn't find anything on Collider. So it means basically the long results of Collider means that the M is large enough. And they have some analysis from the paper from LHC that can give basically a magnitude of this M. Like it's MEV or anything larger, and I actually forgot. Sorry, maybe this is
maybe TV, maybe TV.
Yeah, I would have expected like tens of TeVs as well. So above the current LHC bounds is what you're. I mean, is that what it's supposed to be?
Yeah, I think so.
Okay.
Yeah, but the idea is that if we really observe the large scale deviation from Einstein gravity, and our bounds implies actually the mass gap is pretty small.
Okay.
So
and in this context, I had one final thing, which is like in the context of like large scale deviations from Einstein gravity, why would you suspect that IR physics doesn't have a role in it? Like in the sense of what we were discussing about earlier, because typically large distance corrections are related with IR phenomena, right? And you could expect there to be some small corrections, or there could be significant corrections rather coming from IR effects as a whole.
Yeah.
So
but
why is
IR
this not
effects, so we consider the. I mean, at this stage, we actually can put a value for our IR cutoff. Like we can put the IR cutoff to be something related to Hubble radius, and maybe some science. Maybe some particular scale, and so we can.
So you just set it to be the observable window in the universe, like that's okay. I see.
Yeah.
Okay. Thank you.
Yeah.
So more question? Yeah. Then if no, then we thank speaker again. Yeah. It's very good and nice to have you. Yeah.
Thank you. I'm sorry and sorry for going wrong.
No. It's good. Yeah. So hope everything is okay for you. And if there's some chance in the future, you are welcome to visit us in Taiwan. Okay.
Yeah, sure. If there's a chance. Yeah.
Okay. Yeah. So we will end today's talk. Okay. Thank you very much, Yue-Zhou. Okay. Yeah. Bye.
Yeah. Bye.
Bye.
Yeah. Thank you.
Thank you.